Hello everyone, welcome to Mana CS Classroom. In the previous video, we discussed the classification of data structures and briefly introduced all the data structures in it. Today we are going to learn a very important concept called abstract data type, commonly known as ADT. Interestingly, before learning data structures, understanding ADT helps us understand how programmers think about data structures. An abstract data type or ADT is a way of looking at a data structure. It focuses on what the data structure does rather than how it does it. In simple words, when using a data structure, we are interested in the services it provides. We are usually not concerned about its internal implementation. This is the main idea behind an ADT. Let's take the example of stack. When we use a stack, we only care about operations such as push and pop. We don't usually worry whether the stack is implemented using an array or a linked list. For the user, both versions behave exactly the same. This demonstrates the abstract nature of a stack. The user sees only the functionality. The implementation details remain hidden. ఫర్ ఎగ్జాంపుల్ మనం ఒక ఏటీఎంకి వెళ్ళామనుకోండి, మనకి బేసిక్ ఆపరేషన్స్ కార్డ్ ఇన్సర్ట్ చేయడం, పిన్ ఎంటర్ చేయడం, అండ్ దెన్ విత్డ్రా చేయడం, బ్యాలెన్స్ ఎంక్వైరీ చేయడం, ఈ బేసిక్ ఆపరేషన్స్ అంతవరకే ఐడియా ఉంటుంది. ఆ లోపల బ్యాంక్ సర్వర్స్, ఏటీఎం సర్వర్స్ ఎలా వర్క్ అవుతున్నాయి, ఏ లాంగ్వేజ్లో రాశారు, ఏం ప్రోగ్రామ్ రాశారు, అవన్నీ మనకు అవసరమా? లేదు కదా. సో యూజర్ doesn't bother about the implementation, inner implementation. He only cares about the operations. So to understand ADT better, let's split the term into two words. First, data type. A data type defines the values that it can be stored and the operations that can be performed on those values. For example, an integer variable can store whole numbers, and we can perform operations such as addition, subtraction, multiplication, and division. So, a data type is not just data, it is data together with permitted operations. Now, let's understand the word abstract. Abstract means separating something from its detailed implementation. So, as I told you, when we drive a car, we know how to use the steering wheel, accelerator, brake, and most of us don't know how the engine works internally. Still, we can drive the car perfectly. So, this is abstraction. We use something without knowing its internal implementation. Similarly, an ADT contains the data and the operations that can be performed on that data. For a stack ADT, the user only knows that push inserts the data, pop removes the data, and peep displays the topmost element. The user need not know where the data is stored or how the memory is managed internally. So this diagram clearly explains the concept. The user interacts only with the operations. Behind the scenes, the stack may be implemented using an array or it may be implemented using a linked list. User doesn't care. The user only wants correct results. This separation between usage and implementation is very essential of ADT. So why do we use ADTs? Because programs keep changing. Suppose a student management system stores records using arrays. Later, the number of students increases significantly. A linked list may become a better choice. If we have used ADT principles, we can change the implementation from array to linked list without affecting the rest of the program. This improves flexibility and maintainability. So, a simple example, as I told you, an ATM machine. The user knows only the available operations: withdraw money, deposit money, check balance. User doesn't know how the banking servers process these requests. The implementation remains hidden. So this is exactly how an abstract data type works. An abstract data type focuses on what a data structure does rather than how it is implemented. A data type consists of both data and operations. The term abstract means hiding implementation details. Stacks and queues are common examples of ADTs because they can be implemented using different underlying data structures while providing the same functionality. And next comes algorithms and approaches to designing algorithms. So before writing any program, before coding in C, before implementing a data structure, we first need an algorithm. Let's understand what exactly an algorithm is. An algorithm is a step-by-step procedure used to solve a problem. In simple words, an algorithm is a blueprint for writing a program. Just like an architect prepares a blueprint before constructing a building, a programmer designs an algorithm before writing code. An algorithm tells us what steps should be performed and in what sequence. Let's understand this with a simple example. Suppose someone asks you, how do you make tea? You will explain the steps one after the other. Boil water, add tea powder, add sugar, add milk, and serve. So, these ordered steps form an algorithm. Similarly, computer algorithms also solve problems through a sequence of well-defined steps. A good algorithm must satisfy certain characteristics. Every step should be clearly defined, and then it should finish after a finite number of steps. Third, it should produce a valid output. Finally, it must terminate. If an algorithm never stops, it cannot be considered a proper algorithm. Algorithms are extremely important because they provide software reuse. Once we design an algorithm, the same logic can be implemented in different programming languages. For example, an algorithm designed today can be implemented in C, C++, Java, Python, or any other programming language. Only the syntax changes. The logic remains the same. Interestingly, a single problem may have multiple algorithms. For example, searching a number in a list. One algorithm may search sequentially, another algorithm may search more efficiently. So the question becomes, which algorithm should we choose? The answer depends on time complexity and space complexity. The more efficient algorithm is usually preferred. Large algorithms are often difficult to understand. Therefore, we divide them into smaller units called modules. So this process is known as modularization. Instead of solving one huge problem, we solve several smaller problems. Later, all these modules work together to solve the complete problem. Modularization provides several advantages. The algorithm becomes easier to understand, implementation becomes simpler, testing becomes easier, debugging becomes easier, future maintenance also becomes easier. That is why almost all modern software systems use modular design principles. So there are two major approaches for designing algorithms: top-down approach and bottom-up approach. Both approaches aim to solve complex problems, but they start from different directions. Let's understand them one by one. In the top-down approach, we start with the complete problem. Then we gradually divide it into smaller modules. Each module can be further divided into submodules. This process continues until the problem becomes simple enough to implement directly. This approach is also called stepwise refinement. We start from the top and move towards smaller details. Suppose we are developing an online shopping application. Initially, we consider the complete system. Then we divide it into modules: user management module, order processing module, payment module, database module. Further, each module can be divided into smaller submodules. This is a top-down design. And then the bottom-up approach is exactly the opposite. Here, we start with the smallest modules. After creating these modules, we combine them to build larger modules. Eventually, all modules are integrated to form the complex system. So instead of moving from big to small, we move from small to big. Imagine a software team working on an e-commerce application. Different teams develop different modules: login module, search module, payment module, shopping cart module. Once all modules are ready, they all are integrated together. So this is bottom up approach. So let's compare both the approaches. In top down, we begin with the complete problem and break it down. In bottom up, we begin with small modules and combine them. Top down is easier for planning and documentation. Bottom up encourages reusability and information hiding. Both approaches have advantages and limitations. Now, the question is, which approach is better, top down or bottom up? In practice, most software systems use a combination of both. We first understand the overall structure using top down design. Then individual modules are implemented using bottom up technique. Therefore, real world software development usually combines the strengths of both approaches. So let us summarize. An algorithm is a step-by-step procedure for solving a problem. Algorithms provide the blueprint for writing programs. Large algorithms are divided into smaller modules through modularization. Two major design approaches are top-down approach and bottom-up approach. In practice, both approaches are often combined to build efficient software systems. So thank you for watching. See you in the next class. Subscribe to Mana CS Classroom channel.